Good goodness, where is that? Mm. Good afternoon, everyone. Oh, there it is. I have my tablet that I misplaced for a moment. Hope you guys are having a good day. Today is the 28th, our second class period. Um, I've got your PowerPoint or PDF up on our Canvas page. And today, just I like to think that this is going to give us a little bit of sense of the pace and application and like the use of information in this class. I'm going to share our Canvas site. I'm going to copy and paste it into the chat. So if anyone is confused where I'm pulling this stuff from, then I will give you that reference point. So this is our default choose homepage. Yep, that's our homepage. Sorry, I'm finishing a Cheeto and I will stop eating them. Now, okay. I am looking on Thursday, the 28th. There's amino acids plus water. There's also a PDF. I am going to do my best. I'm going to make a concerted effort to save the marked up version of the class so that wherever there are markings, um, but so when there are markings, they are saved and they are preserved so you guys can see what I marked up. I'm going to make a point to do that. But in the meantime, amino acids and water. So historically, like if you go find a biochemistry textbook, for example, if you're thinking, oh, well, I want a biochemistry textbook because, I'm going to medical school and I want to have a good reference book. To me, this book right here by Voet, and Pratt is a recommended or is a good textbook to have. I do not have any requirements for textbooks, in large part because then it's something that people are purchasing, and I know full well that people use PDFs online. I'll provide links for a reference textbook, an open education resources textbook. It's biochemistry free for all. It's, I guess, published, housed, whatever. I think published by is the most appropriate term by Oregon State University. Um, and you can access that, and that's what I recommend using just because it's free. But if you're like, I like a physical book, I would recommend Fundamentals of Biochemistry by Voet and Pratt. Um, so my point in bringing that up is if you go and get a copy of any biochemistry textbook, whether it's this one, or any other textbook, the first chapter is going to be an introductory chapter. Um, And then the second chapter is more than likely going to be a chapter titled Water. And it's going to bring up the high points about water, things that date back to Gen Chem 1, Gen Chem 2, and organic. Um, I prefer to teach that information and to review that information whenever it's relevant and pertinent. For example, this chapter right here, this chunk of material right here, we're going to be talking about water, but we're going to be talking about it through the lens of amino acids. Same thing goes, we're going to talk about amino acids and we'll talk about them through the lens of water. So that's how I like to do it, just because I feel like it's a little bit more applicable, and application is to me a little bit more important than like, hey, you've seen stuff on water. You remember how to calculate KW, you remember pKa's and pKb's. Great. Here's a little bit of a review. Fast forward. Hey, remember how we talked about pKa's and pKb's? Well, here's that application. What I prefer to do is say, here's our application, and here's a little bit of a review during that application process. Now, with that in mind, if there's something that you get hung up on and you're like, I don't really remember that. Please, you can unmute yourself and speak. You can send me a private message. You can send me or you can send the group chat a full message, anything like that. Feel free. Um, Now, with that in mind, there's one piece of kind of bookkeeping is we will have a poll question today, and I have two monitors, which is why I'm looking over to the left because my actually, you know what I'm gonna do? Okay, there we go. I just moved my camera and it got disconnected for a second. Can everyone hear me all right? Add to the chat a number if you can hear me. Okay, perfect. So we will do a poll question today, just so everyone gets a sense of, well, this is how poll questions show up for me. Um, Specifically if you're using the Zoom app. Okay, so we'll do a poll question today, but I am just kind of giving everyone credit for the first few poll questions before it becomes like a participation thing and important for participation. Then the next thing is starting Tuesday. I guess that would be the third. Um, you'll need to log in to Zoom with your TX State authenticated account. And if you're thinking, huh? I'm going to send a link later today to sort of anticipate that. And that's just going to be so I can keep a more accurate record of who is in class right now. For instance, right now, um, anyone who has the link that I shared can join our Zoom. They don't have to go do a two-factor authentication. Um, and so, yeah, I want to make sure that the people who are enrolled in this class have the specific and unique access to this class. So we'll do that starting on Tuesday. Though I will send the link for how to do that later today. Many of you probably are already logged into that, so you don't have anything to worry about. This lecture is being recorded, so we're good there. Okay, now water. Water, well, mammalian cells are basically 70% or three-fourths water. Two-thirds of our water is inside our cells and a third is outside. Why is water important? Well, water is a universal solvent, and it is a solvent for biological systems. Now, this is important, and this was something that I kind of struggled with all throughout organic and biochemistry. Um, One of the things is that, you know, is pH important in an organic chemistry reaction? Absolutely. But one of the important differences between um, biochemistry and organic is the type of solvent that's used. In biochemistry, we're dealing with an aqueous environment, whereas in organic chemistry, you are dealing with an organic environment. So this is significant because, well, in an aqueous environment, we talk about like ionization and protonation and deprotonation. And we don't, I remember from organic chemistry where it was like, well, this could take place provided that you're using a solvent like hexane. Well, in a biochemical reaction and in biochemistry as a whole, we're talking about everything taking place in H2O, in a water-based environment. Now, with that in mind, things that are hydrophilic will very easily dissolve in water. So polar compounds and ionic compounds, they will dissolve in water. Now, examples of an ionic compound would be something like NaCl, sodium chloride, table salt, will dissolve in solution, will dissolve in a biochemical reaction, whereas in hexane, that's not going to dissolve. Polar compounds, well, water is a polar compound, but so too are amino acids. And we're going to dig into those in a little bit. Um, Hydrophobic compounds are not going to interact with water and they're going to genuinely kind of dislike it. Non-polar compounds are going to not like going into solution in a biochemical reaction. Specifically, where that's important, lipids. Now, what I'd like you guys to think about in terms of, and I was talking about this with one of my earlier classes today. Um, I want you to have like a good idea of a reference compound. And biochemists are really most interested in the following um, biological macromolecules or the following macromolecules. Proteins. Then we're concerned and interested in lipids. We're also pretty interested in nucleic acids. So these are the things that biochemists are, I don't know if I would say most interested in, but these are your kind of hierarchy of like very important things for biochemists. Now, proteins, well, proteins are broken down or made up of AA or amino acids. Lipids, well, lipids are important. They're made up of, for example, fatty acids. And these make up membranes of a cell. And nucleic acids, well, DNA and RNA, they hold together your genetic information. Um, and so these are kind of your important things when it comes to um, what a biochemist is interested in. Now, proteins and nucleic acids, these are things that, for the most part, pretty darn hydrophilic. Lipids, by comparison, are pretty hydrophobic. So if if you're thinking like, I need a good sense of where I can put things over the course of the semester, I want you to try to, almost at the end of every class period, say, okay, with what we covered today, what does that fit into? Does that fit into proteins, lipids, or nucleic acids? Um, I don't want to sound completely and terribly dramatic, but if we have a class period where what we talk about cannot fit into one of these three major categories, I wasted your time. Um, and so what I want you to take away from that is every day in class, it's going to fit into one of these three broad categories. And, yeah, I'll sound a little bit dramatic when I'm saying that, but if it doesn't fit into one of those, then what the heck was the point? Um, and if I can't communicate what the point was related to these three things, then I apologize in advance. I wasted your time. Now, with that said, I don't want to waste your time. I don't want to waste my time. Okay, so those three categories are the big ones. Those three macromolecules are the big ones. All right. Now, with that in mind, polar versus nonpolar. A polar compound is one in which there's an unequal sharing of electrons. Whenever I talk about something being polar or nonpolar and unequal sharing of electrons, what term, thinking about Gen Chem 1, is there any term that comes to mind? I'll give you a hint. It's the one that I'm thinking of starts with an E. And my follow-up is it ends with a Y. Gen Chem 1 term. Thank you. Yeah, I know that's a kind of long term, and I have to make sure that I'm allocating enough time. But electronegativity, you learn about that in Gen Chem 1. Can anyone give me the single letter for the element that is most electronegative on the periodic table, or that you look at as perfect? Fluorine. Fluorine is our most electronegative element. That means that if you share electrons between, if you talk about a carbon fluorine bond or a HF or NF, fluorine. Yeah, fluorine's going to share those electrons, but fluorine's going to want those electrons more than any of those other atoms. Now, if we have like a carbon fluorine bond is a polar bond. A hydrogen fluorine bond is a polar bond. Same thing goes for nitrogen fluorine. Now, polarity is determined based on the electronegativity of those elements. The tendency to attract those electrons, well, it's rooted in all of those. So here what we have is kind of a measure of those different electronegativity values. Does anyone remember who's kind of credited with coming up with these relative numbers for this scale? Thinking of Pauling, perfect, great job. Linus Pauling. The Pauling scale of electronegativity is sometimes what it's referred to as. And these six elements, these six are not just like arbitrarily decided, oh, well, let's talk about those and let's give those values. But instead, these elements are kind of the most important elements when it comes to the study of biochemistry. I mean, thinking back to my journey as a Gen Chem student, I remember being like, oh, cool, we've got, I think at the time it was 112 elements. Oh, cool, yeah, that's great. Do I need to know all of them? And Gen Chem, it was like, yeah, they're all very important. Then you get to organic, and it's like, well, there's really only like five, and five that are important. And in biochemistry, it's kind of the same thing. Oxygen, nitrogen, sulfur, carbon, phosphorus, hydrogen, those are kind of the most important elements. Most of what we will talk about will revolve around these. Now, it's good to have a sense of where those electronegativity values are, but I'm never going to ask you a discrete question or an explicit question. What's the electronegativity value for oxygen? I just want you to think about, well, maybe be able to say a carbon oxygen bond, which chances are it's going to be a double bond, is a more polar bond than, say, a carbon nitrogen bond. Again, I'm not going to ask you to have that calculation ready to go, but I want you to think about the implications of this. Now, when it comes to the electronegativity of these, okay, so this is 2.5, 3.5. Well, this bond is more polar than, say, 2.5 and 3.0. What are the implications of that? Well, if there's more electron density over here where I'm putting this big blob that was once a star, chances are this is going to have a partial negative and the carbon's going to be partial positive. So lots of what we talk about in biochemistry relates to partial charges. And is that region of a molecule more polar or more electron dense than another region? Okay. Can I get a letter in the chat if you're like, okay, good to go, we can proceed? I know that I haven't asked any specific questions, but just want to see, like, is there context? Great. All right. Now, polar bonds in molecules are also known as dipoles. Polar means an unequal sharing of electrons, and electrons ultimately have that negative charge. The atom with the greater electronegativity attracts the electrons, giving that a partial negative charge, which I will always denote with that symbol. If you see that alone, that's a full-on negative charge, not a partial negative charge. The remaining atom in the bond, therefore, has a partial positive charge. So that looks good. Now, each atom of the bond has a different partial charge, thus the term dipole. We indicate that with this dagger symbol. The the pointed end is your negative end, and then the kind of cross or positive region of that dagger, the handle, I guess, of that dagger is where your partial positive charge is. Now, it's important to remember electronegativity, but also to remember that simply the presence of an electronegative or simply the presence of a polar bond does not mean a molecule is polar. Here we've got methane. Methane is nonpolar. Well, in part because the bonds themselves are nonpolar, but more than anything else, it's a tetrahedral molecule. There's no lone pairs of electrons. And, if I did this, F, 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 changed all the hydrogens to fluorines. Okay, well, all these bonds are polar, but the molecule is considered nonpolar because of the fact that it's a symmetrical molecule. Done. Okay, water is a polar molecule because we got those lone pairs of electrons. Those lone pairs of electrons give a partial negative charge up by the oxygen and a partial positive charge by each of the hydrogens. So it's got a bent structure. This is nonlinear, therefore it is a asymmetric molecule, therefore it's a polar molecule. Okay. And so that brings us to kind of the foundation, an important foundation for our discussion of amino acids. Now, this is really important because one field within biochemistry is known as structural biology, predicting the structure of a protein, understanding what a protein's three-dimensional structure looks like. Being able to understand and predict that or know that is extremely important in the field of drug design. If you know what a molecule looks like, then it's conceivable that you could say, okay, well, there's this little crevice in there, and that crevice on the structure, if I designed a molecule to fit right in there, maybe that could prevent that molecule's or that protein's movement, and therefore I could block its activity, in which case you could then regulate like the cell cycle or something of that nature. So we want to understand this so that we can apply this knowledge to higher order thinking and higher understandings. Okay, now this right here is what I touched on the other day. This is our general backbone for a proteinogenic amino acid. Now, does anyone remember, I mentioned this the other day, what is the term used for this carbon? Alpha, perfect. So this is commonly known as our alpha carbon. Now, one thing that's worth noting is that this is the alpha carbon because it's adjacent to a carboxyl carbon. Now, as a follow-up to that, I think a fair question is, well, are there beta amino acids? There are. What do they look like? Well, they look a little bit like this. Okay, so there's our carboxyl, CHH. Here's our alpha carbon, then CH. Here's our R group, our variation. And then here, last but not least, is NH3 plus. This would be an example of a beta carbon. Beta amino acid. Beta amino acids are not that important when it comes to protein structure, or they're not that important when it comes to proteins and metabolism. So these are our alpha amino acids. This is the realm and this is the world that I want you to kind of live within and think about. Now, with that said, I want you to think about this molecule, which is C. Oh, thank you very much. This is our beta. We've got a private message. Which C is beta in the example? So this is our beta carbon. So that would make wherever the R group is, that would designate it as a beta amino acid. Okay, so with respect to this structure right here, we have two ionizable groups. Those two ionizable groups are indicated by those pKa values that I've assigned. This general backbone will undergo protonation or deprotonation. Now, I'm going to give you two options. We've got option A and option B, and I want to see responses in the chat. Option A is that this molecule is drawn at a pH of, let's say, 10. And option B is that this molecule is what it looks like at a pH of 1.5. And before you answer, I want you to think about those two environments. When the pH of a solution is 1.5, there's tons and tons of protons. When the pH is 10, well, then there's not a lot of protons, but there's a lot of hydroxide ions, a very large percentage or a large number of hydroxide ions. There's more hydroxide ions than there are protons. So, given the structure that I've shown, what does this molecule look like? Is this molecule in a solution with a pH of 1.5 or in a solution with a pH of 10? Add that to the chat. And I suppose I'll give you answer option C, neither. But I already asked my question and everyone's giving an answer. And you're absolutely right. B. B is the correct answer. Now, with that in mind, this molecule right here, you could say is doubly protonated because there are two ionizable groups that have both kind of received a proton here and one of those three here. And this molecule has an overall charge of +1. Now, this molecule can undergo a large number of changes. So what I want to do is go through a couple of different examples. We have these two pKa's, 4.8 and 9.3. One very important skill is to be able to know what a molecule looks like under different environmental conditions. And in addition to that, to be able to deduce what's the charge. Okay, so when the environment has a pH of 2.6, if we add this molecule to that environment, what's going to happen is, well, we want to compare the pH to the pKa's. 2.6 is below both of these. So at pH of 2.6, I'm just going to circle it. This is what a very large percentage of that molecule looks like. Could you give me a number in the chat if you agree with that statement? Wonderful. Okay. Now we're going to go on to what about when the pH is 4.8? Okay. So 4.8 is the exact same as one of the pKa's. So, Now, before we begin answering this, one important thing to remember is we're talking about a molecule, or we're talking about a solution with millions of copies of this molecule, moles of copies of this molecule. So if our pH is 4.8, we've basically got two different forms of the molecule. I'm going to say 1 and 2. Form 1 looks like this. NH3 plus. Okay. Then I'm going to complete my backbone. C, C. Form 2. I'm going to draw the backbone N, C, C. And I'm going to take on that N termini, or the amino end. That terminology, I want you to become comfortable with N termini versus C termini. Proteins are read in the N to C directionality. So we've got our N termini, that's protonated. Now, could you give me a letter in the chat if you agree with what I've drawn so far? And a number if you disagree. Okay, so I'm seeing Melanie asks, how are they different? They're not. So far, they are not. So I'm happy that you asked that because they aren't different. And I want you to recognize that the N termini of these two molecules, the two forms of the molecule at this pH, at a pH of 4.8, they are identical. So the N termini is not going to change. Now let's take on our alpha carbon. That has a hydrogen and that has my R group. That's going to be the same because to our knowledge so far, that's not an ionizable group. Now, my C termini, my carboxyl end, this is where we're going to see the difference. One form of the molecule is going to have that proton. So it is going to be protonated. It's going to have an overall charge of +1. The other form of my molecule is deprotonated. And that group is going to be -1, in which case my overall charge from my molecule is 0. So I'm going to write overall charge +1, 0. So now give me a number in the chat if you can see the difference between these two. Great. So the difference is that one's protonated and one's deprotonated. Now a fair question is, okay, so if our pH is 4.8, which is equal to one of my pKa's, then I've got two different forms. And let's just say for simplicity's sake, we've got 1,000 copies of the molecule in this solution. How many of them look like molecule 1 and how many look like molecule 2? First, I'll ask for, tell me in the chat how many of them look like molecule 1 out of the 1,000. How many of them look like 1? Okay, half. Perfect, perfect. So now my follow-up question is, well, how many look like molecule 2? Same number. So I've got an even 50-50 split. So half of them look like this, half of them look like this, half of them look like this. Now my question is, or my follow-up question is, how many of them effectively look like this right here? Effectively 0. Now, a fair question for that is, why? Well, the answer to that is because the concentration of hydroxide ions is pretty darn low. There are not enough hydroxide ions to pick off the proton from the N termini. So this is basically 0 look like this. Is it absolutely 0? I mean, is there a chance that 1 for a nanosecond looks like that? Yeah. But for all intents and purposes, it's basically none of them look like that. Okay, now what I want to do is go on to the next pH. Now we're at a pH of 5.6. Okay, so we've got, I'm going to draw those two forms again. I'm going to draw the kind of the exact same organization. 1, 2. Now, my follow-up question is, give me a letter, a Y or an N. 50% of them look like 1 and 50% of them look like 2. It's a 50-50 split again. No. We don't have a 50-50 split. Now, are both of these two present in the solution? They are. Do we know a ratio? Can you tell me, are there more of one or two? Tell me which one there's more of. One or two? Two is absolutely correct. There are more that look like this than this. And I think that it's fair to say that, well, basically, I think what I'll do is I'll call it about around 80% look like two, and then about 20% look like one. Could I find out the precise numbers? I absolutely could. And the way that I do that is with the Henderson-Hasselbalch equation. The majority of them, though, are going to look like form 2. Now, what's important, and why did I pick 5.6? What's important about this is that, well, does anyone have I'm looking for a word or a concept for why I picked 5.6 as opposed to like 6.5. The word that I'm thinking of starts with a B. Does anyone have that? I'll give you a couple of seconds to try to put it together. Or, or kind of read my mind, basically, is what I'm getting at. What I'm looking for is buffer. A molecule can act as a buffer plus or minus 1 pH unit from its pKa's. So what that means is that when we are plus or minus 1 from our pKa of 4.8, so what that would mean is as low as 3.8 to as high as 5.8, we are within the buffering range of this molecule. And so what that means is that we have a small percentage of this right here and a percentage of this right here. We have both of the forms of our molecule so that a small amount of an acid or a base can be added and our pH doesn't change radically. Can you give me a letter in the chat if you're familiar with what a buffer is? And okay, yeah, I follow. That does make some sense. Okay. So now with that information, now what I'd like to ask you guys is give me a number. How many buffering ranges does this amino acid backbone have? 2. This can function as a buffer between 3.8 and 5.8, as well as 8.3 to 10.3. So if you look at the remainder of these pKa values, let's look at a pH of 7.2. My question for you guys is that within, or sorry, a pH of 7.2, does that pH, or will this molecule right here, will it work as a buffer at a pH of 9 or 7.2? No, it won't. Because our buffering range is from 3.8 to 5.8 and from 8.3 to 10.3. So we're outside of that buffering range. So I got a question. I don't think I understand where you got the buffering ranges. Well, every molecule is going to have a different buffering range. And that buffering range is dictated by the pKa's. So this molecule that I displayed for you guys, I reported the pKa's. And anytime you get a pKa, think, okay, well, one below and one above. That's going to establish my buffering range. So 3.8 all the way up to 5.8 because I did -1 and +1. My other buffering range is going to be by my other pKa. So 8.3, that's where I subtracted 1 from 9.3, and then all the way up to 10.3 whenever I added 1 to that 9.3. I hope that clears up any confusion. So at a pH of 7.2, since this molecule is not going to really work as a good buffer at that specific pH, the majority of my molecule will look like it's been deprotonated at this point. So the majority, the like 99% looks, and I'm sure somebody could do the calculation and say, well, it's actually 99.99999999999999997, and you'd be right. But the majority of it is going to look like this. We're protonated on the N termini, but we're deprotonated on the C termini. Does that make sense? Give me a letter in the chat if that makes sense. Any letter. Okay. Okay, good. I'm seeing lots of responses, positive responses. Now, with that in mind, could somebody make an estimation? What pH will I actually begin to start plucking off this N-terminal proton? We've got a pK of 9.3. Okay, I like your answers. I'm going to tell you, though, it's actually at about 8.3. Now, before you say anything, let's go back a second. And let's look right here. When our pH was 4.8, I'll write it here. I'm going to erase this. When our pH is 4.8, 50% of our molecule looked like this one. And then 50% looked like this one. So it was a 50-50 split at that specific pH. When my pH equals my first pKa, then I have a 50-50 split. Does that make sense? Y or N in the chat? Okay. So now I'm going to jump ahead. When my pH equals this other pKa, I'm going to have, let me ask you this. Give me a number. How many different forms of my molecule will I have when my pH equals 9.3? 2. Now, my follow-up question for you guys, is it a 50-50 split, Y or N to the chat, of those two forms? Absolutely. You guys got that. That's awesome. Now, where it gets a little bit hairy is, but what do they look like? Okay, so in this case, I'm going to draw the two forms, 1 and 2. I'm going to draw the backbone, NCC, NCC, identical. Now, both of these forms, when my pH equals this other pKa, this 9.3, both of them will have a C termini. I see a question in the chat. I'm going to respond to it in just a second. Both of them, the C terminis, will be deprotonated because I've already completely dealt with the C termini. I got a question. So it wouldn't be 50-50 unless one of the pH equals one of the pKa's. Unless our solution's pH is equal to one of the pKa's. Yes, that's correct. Okay. Now, my question for you guys is, do you understand that I've dealt with completely the C termini? Give me a Y or N to the chat if you follow that part. Okay. Now, my alpha carbon, that's going to be the same. H and my R group. H and my R group. My N termini, though, this is where we have our difference. When my pH equal to this pKa, I've got two forms of my molecule. One of them looks like this. One of them looks like this. When my pH is equal to 9.3, 50% is this, and 50% is this. Can you give me a Y or N to the chat if you follow that? Okay. If you follow that, that's fantastic. Now, what I'm going to do is ask you guys to tell me, I'm going to give you percentages. I'm going to say, and I'm going to give you, yeah, I'm going to give you percentages. Now, imagine, I'm going to ask you for a pH. Let's say that 51% of the molecule looks like what is seen for molecule number two, which means 49% looks like molecule one. Tell me the pH where that is the combination. Okay. Okay. I'm seeing good answers. Awesome. I'm not going to say a swear word, but it's fantastic. That is absolutely fantastic. You're absolutely right. That's the direction that I'm going in. Because what if we look at molecule number two here? That's doubly deprotonated compared to molecule number one, which is only singly deprotonated. So what pH are we going to get that at? Well, if you think about pH as acidic or basic, it's going to be the more basic pH. Well, more basic than what? More basic than 9.3. So I see answers of 9.4, 9.5. You're absolutely spot on. Now, if I were to flip it and I were to say, okay, well, rather than it being that, what if it was 52% this and 48% this? Nope. Well, then your answer is going to be, okay, so our sample that is in a higher concentration is number one. So that means we have a more acidic. Yes, 9.2, 9.1. Yes, awesome, 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 awesome. Okay, now in the event that, or if anyone is thinking, well, this is just Gen Chem 2. I know this. Good, good. That's exactly what I want you to be feeling and thinking right now. I think that historically, there have been times whenever I've taught this class where someone will say, like, well, that's just review stuff. I know that already. Yeah, awesome. That's great. If I had a, I don't really know where I would go if I had a dollar dot dot dot, but think about how much information you've been exposed to in your life that you don't remember. Okay, that happens. So when you remember information and you've like, it's in your head, it's embedded and you get it, awesome. Celebrate that. That's great. That's not like trivial. And this is tricky and abstract. Now, my next question related to this is not what does this look like, but at a pH of 10.9, would this molecule right here that I've put a big circle around, would that work as a buffer at a pH of 10.9? Think about the buffering range that this molecule can work at and add a Y or an N to the chat. Awesome. No, it could not because the buffering ranges for this molecule are 3.8 to 5.8 and 8.3 to 10.3. 10.9 is outside of that buffering range. So that's awesome. That's not a trivial thing, and buffering is kind of tricky and strange to wrap your mind around. Now, with that in mind, one of the things that I always like to bring up to send home the point of a buffer, um, there's your blood. Your blood is very resistant to pH change. And that's because there's something known as bicarbonate that acts as a buffering reagent in there. So it helps maintain your blood pH. Um, and your blood pH is going to be about 7.14, we'll say. Would you want this molecule right here to help buffer your blood against any sort of pH change? Y or N to the Chad? No, you wouldn't. Okay, I got a message that was a little longer. You wouldn't, because if you want your red blood cells to be in a solution with a pH of 7.1, this molecule is going to do a very, very bad job of doing that. If it's in its buffering range, would it be 50-50? That's a great question. It's 50-50 whenever your pH is equal to the pKa. If you go above that, that 50-50 balance sort of shifts. Okay. So when we look at proteinogenic amino acids as a whole, what I will almost always do is I will always draw them where they are fully protonated. That's most helpful for me. Anywhere that I can put a proton, I'm going to. So whenever I draw whenever I draw a proteinogenic amino acid, I'm going to draw it at a pH of 1. And then what I'm going to do is I'm going to take the pKa values that I'm provided with, and I'm going to rank them from lowest to highest. So I'll say 4.8 and 9.3. And I'll say, okay, well, when my molecule is at a pH below 4.8, this is what it looks like. When my molecule, or that's what the majority, let me clarify, the majority of it looks like that. A term that you'll hear me say from time to time is predominant. So if my pH is between 4.8 and 9.3, the predominant form looks like this one in the middle. And then if my pH is above 9.3, the predominant form of my molecule looks like this. Okay. Now I'm going to give you some answer. We'll do kind of lightning round. Whenever I was a kid and I'd had spelling bees, I remember sitting at the kitchen table with my dad before I get on the bus, and we do lightning round. It was really a wonderful memory of mine. So, we'll go lightning round. I'm going to give you a pH, and you tell me which form or which of these molecules is the predominant form. 10.2, is it A, B, or C? Okay. 1.6, is it A, B, or C? 4.9, is it A, B, or C? 9.1, is it A, B, or C? 9.4, is it A, B, or C? Okay. So the majority of the answers were very good. I think that some people were maybe answering the question that I had previously asked, but anything below 4.8, it's going to look like this. Anything above 4.8 and below 9.3 looks like this. Anything above 9.3 looks like this. So I want you to think about, okay, well, did he say anything about specifically 4.8? No, I didn't. Because whenever your pH is equal to 4.8, which in this case is our pKa, then the predominant form looks like this and this. When it's 9.3, well, then it's this and this. There's not one single predominant form. When I say 4.79, A is the predominant form. Does that mean there's no B in there? No, that just means that 50 point 50.1% of the molecule looks like A at 4.79. And then 49.9% looks like B. Okay, so this is the ionization stuff about amino acids. Understanding pK, understanding how these groups are protonated and deprotonated. Now, one thing that I want you to remember is the carboxyl group, which, yeah, I can clear all my writing on here. Perfect. This group right here, that can be neutral or can have a negative charge. The end. It's not going to be positively charged. It's not going to be -2. In the event that it were, then you're kind of destabilizing the whole entire molecule. So that's your C termini. The N termini group here. Well, it's either going to be positively charged or neutral. It's not going to be +2. It's going to be +1 or 0. It's not going to be -1. It's going to be +1 or 0. Now, the R group is the part of this that we haven't really talked about. And that's because it just kind of opens a Pandora's box of other information. Now, with that in mind, I want to introduce these R groups in a gradual fashion. These R groups are going to be classified as either polar or nonpolar. Now, when it comes to classifying your proteinogenic amino acids as polar or nonpolar, let me tell you, we ignore the backbone. And that's for the classification. So whenever I show you this next slide that shows polar, I am ignoring the backbone. Can you give me a number in the chat if, okay, I follow that. I'm only concerned with the R group. I saw somebody put a J down. Presume that that's just, okay, I'll get there. So here are your polar amino acids. One thing I want you to notice is that, well, we've got kind of a diverse group here. Boom, boom, boom. Okay. And if you sort through this list, you're going to see, okay, well, there's 11 amino acids that are classified as polar. Then if I go to the next slide, there's 9 that are classified as nonpolar. Okay. Now, eventually, you'll know the structures for all of these amino acids. Do you know them today? Some of you probably do because some of you are preparing for the MCAT, taking that maybe in the spring or something like that. In which case, fantastic. That's going to be helpful for you. Others, not quite yet, but you're going to get there. Now, what I think is most valuable when it comes to knowing your amino acid structures is you need to be able to classify them. The classification is exclusively to the R groups. You also need to understand ionization. That's absolutely important because what do we know in any chemistry class? What we really want to know about is interactions. What does a positively charged group typically interact with? Positively charged functional group, we'll say. A positively charged functional group is going to love to interact with a negatively charged functional group or a partial negative functional group. So we need to know what these different molecules look like at a different pH so that we can understand interactions. Now, the way that I like to approach learning your amino acid structures is I like to approach it as I'm going to show you all of these molecules when they are fully protonated. So these are what they look like at, and tell me in the chat, do you think this is at a pH of 1, 7, or 10? Add to the chat your answer. These are what the molecules look like at a pH of 1. It's easier for me personally to think about them in extremes. These are as protonated as they are possibly going to get. We know the backbone. Those are two groups that are going to be deprotonated. Now, whenever I go to the next slide, I'm going to show you the nonpolar amino acids. These nonpolar amino acids, when you kind of dig down and you look at something like valine or alanine, those two R groups are hydrocarbons. How would you classify a hydrocarbon? Polar or nonpolar? Nonpolar. So with that in mind, do you think that these R groups are going to participate in ionic interactions? Probably not. What about hydrogen bonding? Are they going to be good candidates for hydrogen bonding? No, probably not, because when we talk about hydrogen bonding, remember you got to have an OH or a NH, and you got to have some lone pairs of electrons. CH, not a good combination for because, well, it's not a polar of enough bond. FH would also work, yeah. So we've got to have hydrogen, but then we also have to have N, F, or O. And these guys, no N, F, or O in those R groups, so not good for hydrogen bonding. And if you're thinking, oh crap, I don't remember that, don't worry, we're coming back to it. So these are your polar amino acids, these are your non-polar amino acids. We're going to work through them kind of deliberately on an individual basis. So don't worry, we're going to revisit all of them and look at them individually. Now, with that said, when you look at these groups, are there any other groups that you can see? Well, I know that these images, you might have to zoom in on them a little bit, but one thing that is important to know is that there's a third category of your amino acids based on their R groups. And my hint is that there's one polar and there are two that are nonpolar. So two nonpolar amino acids and one polar amino acid, they come together to make this third group. And it's a little bit tricky to see, but where I'm going with them is, well, boom, boom, boom. These three amino acids make what are known as your aromatic amino acids. So sometimes you'll hear amino acids grouped into polar, nonpolar, and aromatics. And it's these three, tyrosine, tryptophan, and phenylalanine, that make up your aromatic amino acids. Now, I want you to, looking on this next slide, there's a couple of, I've got this question. What do you notice about these amino acids? And before you answer, what I want you to remember is that these are fully protonated. Is there any group of three that stand out to you as having a similar trait or as having a similar property? And I'm going to narrow your scope a little bit. Think about types of interactions that they could have. Where I'm going with this is these three right here. Looking at their R groups, I'm going to scribble out the backbone. Is there anything that you notice about those R groups? Hint is a small marking. Aha! Nitrogen with a charge. Perfect. The charge, yes. These three amino acids, lysine, histidine, and arginine, are your polar positive. Perfect. Great job. Okay. So with that in mind, There's another group of amino acids, these two right here, aspartic and glutamic acid, that make up your polar negative amino acids. Now, when you look at those R groups of those two amino acids, aspartic acid and glutamic acid, um, do you see a negative charge, Y or N in the chat? No. You're correct. There's not one. What's important to know is that, and to recall, is I've got these drawn at a pH of 1. So this definition of polar negative, or this negative, is at a pH of 7. These groups will be negatively charged. So that definition, polar negative or polar positive, is related back to at a pH of 7. That's where that comes from. Now, those are your polar positive amino acids. So whenever it comes to learning your amino acids, one thing that people have a tendency to do is they say, okay, cool, 20 amino acids. I'll learn those structures in a heartbeat. And they make their flashcards and they get their Quizlet and they're like, done. And then they're like, well, I have all the materials, so I should know this. And of course, I'm referencing myself because I would get all my materials and then be like, okay, cool. Well, now it's in my head, right? No, it was never in my head because I didn't really study it. I would just be like, I think I got it. Um, don't fall into that trap. Don't try to consume all 20 of them at once. Instead, break it down a little bit and say, okay, here are my polar positive amino acids: lysine, histidine, and arginine. What do I see that's similar about these two? Well, lysine and arginine, they both have this kind of long alkyl chain. Lysine has 4 carbons, arginine has 3 carbons. And then arginine has this crazy functional group that's NC, NC. Okay, throw some hydrogens on there, and that's where I'm going to get my positive charge. Lysine, by comparison, is 4 carbons and then an NH3. Histidine, well, this has a ring. This is known as an imidazole ring. So my point is not necessarily, oh, you have to remember imidazole ring, but instead to look at these individually and say, okay, what does lysine look like? Okay, can I draw the backbone? If you can feel comfortable drawing the backbone of an amino acid, you're going to be in great shape. Then, when it comes to drawing the R group, well, 4 carbons and then an NH3, lysine, done. Arginine, 3 carbons and then this NCNN, done. Now, I know by just saying done does not mean that you understand it and it is done, but I'm just trying to communicate, like, there's a step, there's a process, or there's steps to this, as opposed to just like, yeah, go out and learn it. Now, your polar negative amino acids. What functional group do both of these R groups have on them? Carboxyl. They both have a carboxyl group. Now, let me tell you that more times than not, people will come up with very good mnemonics for grouping amino acids. And from my own experience, the best mnemonics are the ones that are the ones I can't say in class because those are memorable. Whenever I think of aspartic acid and glutamic acid, I always think of them for some reason as siblings. And I think of them as, well, glutamic acid is the taller of the 2 siblings. That helps me kind of put this information together in my head. Now, what's important about these amino acids is, in addition to their structure, they also have identifiers. They have 3-letter and 1-letter code identifiers. Lysine, LYS. Histidine, HIS. Arginine, ARG. These 3 amino acids use the first 3 letters to put together their three-letter code. The single letter code. K. What? That doesn't make any sense. H makes sense, and R makes sense. A fair question is, where did these identifiers come from? Well, they came from the work of this woman right here, Margaret Oakley Dayhoff. Margaret Oakley Dayhoff was a bioinformaticist and a biophysicist back in the 1950s. And she was doing um, studies of protein or energy associated with proteins and their dynamics, how they move and how much energy was associated with these movements. And she was doing this and programming it into a computer and was like, when you write the full name of the amino acid to put together the structure of a protein, it's really kind of a burden. It's tough to work with. And so her work led to identifying amino acids as single letters and three-letter codes. And they came up with the IUPAC and came up with rules. And those rules were, when available, use the first three letters of the amino acid's name to identify it. And then, when available, use the first letter to give the first letter code. But obviously, when you have amino acids like aspartic acid and alanine, they both have the same first letter. So that's whenever they would implement like a phonetic pronunciation. And they'd say, what's the hard consonant in aspartic acid? And they came up with D. Then glutamic acid, well, structurally is very similar to aspartic acid. And so they just use the follow-up letter E for that. So what I want you guys to be thinking about and taking away from today is I want you to begin looking at and learning the structures for your polar positive amino acids, your polar negative amino acids. Can you give me a number in the chat if you follow that? Okay. Now, to help all of this come full circle, what I'd like to do is give all of those 5 amino acids, your polar positive and polar negatives, they have ionizable side chains. What I would like to do is look at the different structures of aspartic acid that exist at different pHs. Can you give me a letter in the chat if you follow the similarities or the connection between this and what we've done with just the backbone? Okay. Now, my question before I begin is, how many buffering ranges does aspartic acid have? Or buffering ranges. How many buffering ranges does aspartic acid have? It's got 3. The N termini, the C termini, and the R group. Okay. Now, before we begin, this structure right here that I've got, what pH is that drawn at? pH of 1. Because everything is protonated. Now, what I want to do is I want to find aspartic acid, single letter code is D. The lowest pKa is 2.1. The next lowest pKa is 3.86. The last pKa is 9.82. 2.10, 3.86, 9.82. How many? Okay, so then this form right here, I'm going to draw it, NH3. Sorry, I got to give myself a little bit more space. So what I'm going to do is I've got three ionizable groups. Therefore, there are going to be four different possible structures that this molecule will have. I'm going to go with N, C, C. Draw my backbone. I just want to start out with this, and then I will fill these in individually. I want to start out with all of them, but then individually fill them in. So all that I'm doing is when my pH is below 2.1, I'm going to draw this form of a molecule. So NH3 plus my alpha carbon, H. Then here's my ionizable R group, C, C, carboxyl, OH, H2. Then my C termini, O, OH. Okay, give me a letter in the chat if you follow what I did there and you're good with that structure. Okay, now what I'm going to do is imagine that I'm adding more base to this situation, adding some sodium hydroxide, a strong base. Now give me a number in the chat. Which group with my pKa's, pKa of NH3 is 9.82. The pKa of my COOH, my C termini is 2.1, and the pKa of my R group is 3.86. Which group am I going to be deprotonating first? The 1, the 2, or the 3? COOH is right, but in this specific molecule, I've got two of those. Perfect. It's 2. That group is going to be deprotonated first. So the result of my molecule is going to look like this. NH3 plus. Onto my alpha carbon, H, CH2, C, O, OH, and then O, O minus. Give me a letter in the chat if you follow that. Okay, I got a private message that says, can you clarify why it would be first? Well, the reason that it would be first is because it has the lowest pKa value. Okay. Now, referencing the first molecule that I drew right here, which group am I going to deprotonate now, thinking about the pKa values? 3. You're absolutely right. So now my molecule looks like this. The C termini is deprotonated. I've dealt with that completely. Now I'm on to my R group, CH2, C double bond O, OH. Oh, not OH, Joel. O minus. Okay, can you give me a letter in the chat if you follow that? Great. So I'm going to start on the right-hand side of my molecule. O minus, H, CH2, C double bond O, O minus. What's left? What should this look like? What should I write down here? Perfect. H2. Done. Okay, can you give me a number in the chat? A number greater than 10 if you follow what we see. I got a private message. Are we seeing the structure based on different pH? Yes, we are. Because imagine that I'm more adding hydroxide, sodium hydroxide, potassium hydroxide, increasing the pH from 1, which was on the far left, to greater than 9.82, which is on the far right. Okay. So now I'm going to erase some of this. And I'm going to label each of my molecules. A, B, C, D. I'm going to put a little arrow below my number there, my pKa values. And if you have to leave, you can leave. I don't want anyone to feel like I'm trapped in biochem. We're going to begin class with this on Tuesday, just because this is a skill that needs to be built and developed. So we're going to be doing this skill starting on Tuesday as well. But now my question for you guys is tell me which forms of my molecule are present if the pH of my solution is 3.7. I'm looking for two letters. My pH is 3.7. 3.7 is right here. I should have B and C. I shouldn't really have any A present because I've dealt with the C termini. Okay. Now let's imagine, oopsies. Let's imagine that my pH is, let's try this, 9.3. What forms of my molecule, or actually let me rephrase, oh, okay, C and D. Good. If my pH is 9.9, how much A is in there? Give me a percentage. Okay, 0. I agree with that. How much B is in there? Basically 0. Yeah. Now, this is a little bit tricky because we've gone from 9.9. Let's say our pH is 3.9. Our pH is 3.9. How much A is in there? Basically 0. The important part about this is placing 3.9 along this 3.9. We are slightly above this pKa. So basically 0 of A and basically 0 of D. At 3.9, you're looking at like 55% C and 45% B. Okay. We're going to pick this up again on Tuesday. So we'll probably do the exact same example and then work through some more examples. In the meantime, though, I hope you guys have a great weekend. I forgot to do a poll question today, but that's kind of no consequence because everyone's getting credit for these first few days. Remember on Tuesday to come to class with your authenticated login. And I hope you guys have a great weekend. Thanks for coming.
I had a question. I'm sorry.
If you have a question, I'll let everyone else depart, and then I'll hang out and answer your questions if that's all right.